Okay, well, thanks very much. Hi, everybody. My name is Dimitri Veras, and I am based in England at the University of Warwick. I thank the organizers for giving me the opportunity to speak here at the Hellenic Astronomical Conference, and I'm happy to learn about the astronomy research which is being conducted at universities throughout Greece and elsewhere. My research primarily concerns the theory of planetary systems, similar to Nikos Georgiakarakos, who spoke earlier today. And a particular research focus of mine is the fate of planetary systems, or in other words, what happens to planetary systems when they are in their death throes after their parent stars leave the main sequence. And so before discussing our specific project, I first would like to provide some background information about this topic. So our sun is a middle-aged star that will leave the main sequence in about 6 billion years. So when the sun or any main sequence star leaves the main sequence, it undergoes significant transformations. So the sun will lose about half of its mass through winds. The sun's radius will expand out to about where the Earth currently sits, and the sun's luminosity will increase by a factor of thousands. Then the sun will shrink down into an Earth-sized object known as a white dwarf. And a white dwarf is comparable in size to the Earth, but contains about half of the mass of the sun. And as a result, the surface gravity of a white dwarf is 5 orders of magnitude higher than that of the Earth. And such a high density allows the white dwarf to probe planetary systems in a unique way when the planetary material actually falls onto the white dwarf atmosphere. So what are the consequences for the solar system when the sun leaves the main sequence? Well, Mercury and Venus will be engulfed. The outer planets and Mars will survive, and Earth will be right on the edge of being engulfed. There are also interesting consequences for the minor bodies in the solar system, which will be broken up and shifted around due to radiative effects known as the Yorp and Yarkovsky effects. And so after the sun has become a white dwarf, we're left with at least 5 major planets, many minor planets, and lots of debris. And at this stage, various processes can transfer the debris to the solar white dwarf. The processes are both radiative and gravitational. And one of the most common processes is thought to be gravitational scattering between the planets and the asteroids, such that the planets kick the asteroids onto highly eccentric orbits towards the white dwarf. And these gravitational perturbations can occur multiple times over billions of years after the star has become a white dwarf. And after being kicked towards the white dwarf, these asteroids they break up at the white dwarf Roche sphere and form a disk. And this disk material eventually becomes gas through some combination of collisions and sublimation, and then that gas is accreted onto the star. Now, what's remarkable about this accretion is that we can easily pick out its chemical constituents. Because the density of a white dwarf is so high, the star chemically stratifies all accreted material, and these so-called metals can then be seen amongst the backdrop of just hydrogen and helium. As a result, we can perform chemical autopsies of these exoasteroids. And so far, as you can see on this periodic table, over 20 different planetary metals have now been detected in the atmospheres of white dwarfs. And overall, 1,000 white dwarfs with planetary debris in their atmospheres. And this debris is similar in bulk chemical composition to the Earth, with high fractional abundances of oxygen, iron, magnesium, and silicon. Now, there are some striking exceptions of asteroids which are water-rich and to a significant extent. So some of these progenitor asteroids contain mass abundances of water then at the tens of percent level. Also, this high level of detail in chemical composition allows us to make inferences about the extent to which progenitor asteroids were differentiated and where in the protoplanetary disk they were actually formed. Now, accompanying these metal white dwarf atmospheres are the disks or rings that are formed by these incoming and disrupting asteroids. And we know of over 60 of these disks, which are composed of both dust and gas. And at least some of these disks appear to be eccentric and wispy and variable, sometimes featuring outbursts. Now, we also see the individual asteroids themselves. In now over a half dozen cases, minor bodies have been detected orbiting white dwarfs. And most of these minor bodies are in some state of ongoing destruction. and also in a bewildering variety of orbits. And finally, we know of 4 major planets that orbit white dwarfs. So you might ask, why only 4? It's because they're hard to find, but many more are likely to be present. But the point is that we now have observations of metal-polluted white dwarfs, disks and rings orbiting white dwarfs, minor planets, and major planets orbiting white dwarfs. And one significant question is, what is the geometry of the asteroid encounters with the white dwarf Roche sphere? And what can that tell us about the architecture of the system? And so to answer that question, in our project, we performed a suite of n-body simulations with the simple setup that you see here. We began with the star at the end of the main sequence, a belt of asteroids, and 1 planet. And the asteroid belt is located at 3 to 10 AU, which is a distance range where the asteroids would survive the outward expansion of the star during its giant branch phases. The planet is further away at about 10.5 AU, and the evolution of the star will create gravitational instabilities between the planet and the asteroids, allowing the planet to kick the asteroids into the eventual white dwarf. And we use the code which evolves the star and planetary systems simultaneously, such that the star traverses all of the giant branch phases of evolution while the planet and asteroids interact with one another. And we sampled 3 different eccentricities and 5 different masses for the planet and placed all of our results in the context of those variables. So I'm going to give you the punchline of our results first and then describe our secondary results. So now to understand our results, I'm first showing you our geometry. The pericenter of the planet's orbit is in the x direction, as you see here, and the planet's orbit is in the z=0 plane. So the asteroids are initially nearly coplanar with the planet, but not exactly coplanar. And this non-coplanarity is important and is magnified as the interactions with the planet propagate during the stellar evolution. So here are the results. These plots are the punchline. Each grade here is a projection of the white dwarf Roche sphere, and the dots are the locations of the asteroids at the last time step before entering the Roche sphere. Each dot is connected to the white dwarf with a blue line for visual effect. And the different rows correspond to different planet masses, whereas the left and right halves of this slide correspond to different planet eccentricities. So what this collage illustrates is that there exists a correlation between the geometry of asteroid injection and the planet properties. And the effect is greatest for the lowest mass planets. Then as the planet mass increases, the tidal encounter geometry becomes increasingly isotropic. However, the correlation of isotropy with planet eccentricity is weaker. As you can see, there's not too much difference between the left and the right halves of this slide. So now that I've shown you the punchline, I'll present some ancillary results. So here are the outcomes for the asteroids when the planet is on a circular orbit for a 20 Earth mass planet. The x-axis shows the initial asteroid semi-major axis, and the y-axis shows the initial asteroid eccentricity. The symbols show only unstable outcomes, and the entire area under the black curve represents the initial conditions for the asteroids. The blue triangles are asteroids which escaped the system, and the black squares are those which collided with the planet. There are no red star symbols here, which would indicate that the asteroid hit the white dwarf. And so this plot helps illustrate that planets on circular orbits cannot produce this white dwarf metal pollution. So now if we increase the mass of the planet, here is the result. Here for a planet mass of 300 Earth masses, but still on a circular orbit. We still don't see any asteroid collisions with the white dwarf, and instead we see more structure in the asteroids which escape the system. And the locations of many of these asteroids correspond to strong mean motion resonances with the planet. And by resonance, I mean when the orbital period ratio between the planet and the asteroid is a low integer ratio. So for example, every 3 orbits of the asteroid correspond to every 2 orbits of the planet. That would be a 3-to-2 resonance. And these resonances are indicated by dashed vertical brown lines. So now let's see the results when the planet is on an eccentric orbit. So here the planet's orbital axis is 0.2 and the planet mass is 1 Earth mass. And as you can see, nearly all of the instabilities here correspond to asteroid encounters with the white dwarf. And the reason why we see so many red stars and not blue triangles is because the planet is not massive enough to scatter the asteroids out of the system. And so for this particular simulation, we were then able to obtain substantial data on the geometry of asteroid injection into the white dwarf Roche sphere. So we really had to rely on the simulations with eccentric planets to obtain this data. So now I'm going to gradually increase the planet mass and show you the results. So the planet mass on this slide is 1 Earth mass. Next, I'll go up to 5 Earth masses. So you can see more instances of escape here. And now I'll go up to 20 Earth masses. And here is the result, where you begin to see more structure in this instability plot. So now I'll go up to 100 Earth masses. And here you can really start to see resonant structures at a variety of different resonances, which are labeled on the top x-axis. And finally, I'll go up to 300 Earth masses. And here you can see that most of the asteroids which hit the white dwarf are associated with the 2-to-1 and 3-to-1 resonances with the planet. Alternatively, the asteroids associated with escape from the system, the blue triangles, are outside of these strong resonance locations. Now, besides these instability portraits, I will now show you some other results of the simulations. One of these results is the escape speed from the system. So here's a plot of the escape speed versus instability time throughout the giant branch phases, denoted by GB, and the white dwarf phase, denoted by WD. So as you can see, the escape speeds are very low, on the order of 0.1 to 1.0 kilometers per second. And the variation in these speeds with instability time are about 1 order of magnitude. Now, in contrast, we can plot the asteroid speed at the white dwarf Roche sphere, which is much faster at nearly 500 kilometers per second. So here's the y-axis. Here, the y-axis is the encounter speed, and the x-axis is the orbital pericenter of the asteroid orbit at the Roche sphere. So you can see that the encounter speed for the asteroids is just under the escape speed at the Roche sphere, given by the blue horizontal line. You can also see that most asteroids have grazing encounters with the white dwarf Roche sphere because the symbols appeared clustered on the right side of the plot. Now, the statistics of this clustering revealed that only about 1% of asteroid encounters would result in a direct collision with the white dwarf if those asteroids could actually survive the passage through the Roche sphere to the stellar photosphere. We can also look at the times at which the asteroid enters the Roche sphere. These times then translate into debris disk formation timescales because the asteroids break up to form these disks. So here are plotted 4 curves for different planet masses and eccentricities, where each curve displays a different disk formation timescale distribution. The top 2 curves are for a 300 Earth mass planet, whereas the bottom 2 curves represent a 1 Earth mass planet. And the lower planet masses allow for a more steady distribution of formation times because the gravitational force of their perturbations on asteroids is smaller than the corresponding force for the larger planet masses. So in conclusion, we modeled planetary systems whose parent stars have left the main sequence. We considered the interaction between the asteroids and planet in these systems as the star traversed the giant branch and white dwarf phases of stellar evolution. And our specific goal was to analyze the geometry and velocity of asteroids as they entered the Roche sphere of the white dwarf. We found that lower planetary masses increases anisotropic injection into this Roche sphere. And to show you once more, here's the punchline plot again, whereas the lower planetary masses, which are shown in the upper rows here, increases anisotropic injection. In contrast, the higher planetary masses displayed in the bottom rows illustrates largely isotropic injection into the white dwarf Roche sphere. So as a result of these plots, we can use Roche sphere dynamics to make inferences about planetary system architectures. Thanks for your attention.
Okay, thank you very much, Dimitri. I'm actually going to start with the first question. Is the problem much, when you're looking at the fraction of asteroids going in and the fraction being ejected, isn't that similar to the dynamics that's been studied in the beta pic falling evaporating bodies scenario by, for example, Buist and Morbidelli, who invoked a planet where the resonances, the 3-to-1 or 2-to-1, or the mean motion resonances could account for the number of falling evaporating bodies. Is that generally the same type of dynamical problem, or are there differences?
So that in one sense, it's the same type of problem because they've analyzed the fraction of bodies that actually encounter the star, which you don't normally see in main sequence studies. The difference, though, is that when the star leaves the main sequence, it changes the dynamical stability boundaries of the system. And so the stability boundaries used in the beta PIC studies were not the same as the ones used here, because the mass loss from the star actually changes criteria such as the Hill stability criteria and the Lagrange stability criteria. So that means the various separations will be different and the timescales will be quite different. Because beta PIC is, well, I don't know. Do you remember, Paul, how old beta PIC is?
Oh, it's 24 million years, and it's a 1.8 solar mass star.
Okay, so 24 million years. Here we're referring to simulations which lasted billions of years, and in many of our other studies, we actually simulated these systems over 14 billion years. So it's almost 2 to 3 orders of magnitude difference in terms of time scale, as well as a difference in terms of these stability boundaries. Does that answer your question?
Yes, thank you.
Okay.
Yeah. I was there's a Buste and Morbidelli paper of 2000 that came to mind as I was looking at your plots.
Thank you. Yeah, I actually don't remember that specific paper, but I'm always looking for more examples of main sequence studies that actually consider the collisions of small bodies with stars, because that's often not the focus. But with exocomets, that is particularly relevant. Usually those dynamical studies consider collisions between the planets or ejections of planets. But as I've shown you, the actual collisions with the white dwarf are so important because they produce so many of the observables.
Okay, we have time for questions. Still more time. And I saw your review paper is on AstroPH, so people can go to it just to probably has the plots, many of the plots that you talked about. Yeah,
that's right. Yeah, thank you for pointing that out. It is on archive now. Yes.